All right, let's talk about material equilibrium now. If you recall, we said that a system is at equilibrium when it's at thermal equilibrium. That means its temperature is well defined and it's uniform throughout. It must also be at at mechanical equilibrium, which means that it's a well-defined pressure. So it has a well-defined temperature. It's at thermal equilibrium. Condition number two is it has to be at mechanical equilibrium. Its pressure is well defined, and external pressure equals the pressure of the system, so the wall will have no tendency to move. And the third condition for equilibrium is material equilibrium. That means you're dealing with a system where the composition would be fixed. So if there is any chemical reaction going on there, then that means the rate of formation of products will be equal to the rate of formation of reactants. So even though at the molecular level changes are occurring, at the macroscopic level, nothing appears to be changing. If there's a phase transformation going on, if you have, for example, molecules of water going from ice to liquid water, that would have to be equal to the rate at which molecules from the liquid go back into the ice when there's material equilibrium. So you will not see a net change in the composition of your mixture. All right. So to understand material equilibrium, we need to understand the concept of chemical potential. Chemical potential is similar to pressure and temperature. Okay. So the important property you deal with thermal equilibrium is temperature. With mechanical equilibrium, we deal with pressure. Now, when you're interested in material equilibrium, you have to understand what's called the chemical potential. Now, we're going to define chemical potential in just a short while from the fundamental equation of thermodynamics. But at this point, we're just going to try to get a qualitative feel for exactly what this is. Okay, so we can define qualitatively chemical potential as the measure of the tendency of a species, which could be an atom, a molecule, or an ion, to disappear from a system. Okay, and there's basically two ways an atom, a molecule, or an ion can disappear from a system, and that's one way is by chemical reaction. So a reactant molecule can disappear, and you get product molecules as replacement, or you can have an atom or a molecule or an ion just physically moving out of your system. Okay. Now, we define chemical potential such that if the chemical potential is higher, then it's more likely to disappear. So it's like temperature. The higher, you can think of temperature as a heat potential. The higher the temperature, the more likely your energy is going to move out of your system as heat. Because like if you were to put something hot next to something cold, what do we know? Heat flows from the hot object to the cold object. In a similar manner, a higher chemical potential would involve a situation where your species, if it's got a high chemical potential, it will have a higher tendency to disappear. Okay, so the consequence of this is that a species tends to move from a system where its chemical potential is higher to one where it is lower. Consequence of this, as far as chemical reactions is concerned and chemical equilibrium, we'll deal with that in another lesson. Okay, so for this lesson, we're just going to focus on phase equilibrium, movement of chemical species without chemical reactions being involved. All right, so our experience with chemical potential suggests that if you're dealing with the same phase, the chemical potential is higher the higher the concentration or the pressure at the same temperature. Okay, and that the chemical potential would be lower at higher temperature at the same pressure. And that's a good way to remember this is this. The higher the concentration, the higher the pressure. Imagine yourself in a more crowded room. So there's more people like you in the room. You have higher tendency to disappear from that room. That's just an analogy. It's a good way to remember it. And chemical potential is lower at higher temperature. Think of it this way: the hotter the room, the more chaotic the movement of the people in the room, then you're more likely to disappear from that room, more likely to leave. Okay. So here's an illustration of the concept of chemical potential. Let's say here you have two compartments, one both containing a dye molecule, a solution of a dye. So on the left-hand side, on the left compartment here, you have 0.1 molar solution of the dye, and you have a 1 molar solution of the dye on the other side, on the right side. Now, what if we were to remove this barrier right here, take it away? What would be the what do we expect to happen? We're going to expect mixing of the two solutions, and eventually, what do we expect? The dye molecules will spread out. There's going to be some net movement of dye molecules in which direction? It's going to be from right to left, right? It's going to be. So we're not saying that none of these dye molecules on the left can go to the right. They are all free to move about, but overall, we say there's a net movement of dye molecules from the right to the left based on our experience. So right to left would be the net direction of the dye molecules. So on which side then is the chemical potential of the dye higher? So what do we say about chemical potential? A species has a tendency to go from a system where it has a higher chemical potential to one where its chemical potential is lower. So the chemical potential here is higher. So let's call this mu right and mu left. So the chemical potential on the right is higher than the chemical potential on the left. Okay? So you can see that the higher the concentration, the higher the chemical potential. Let's look at this example right here. Let's say you have liquid water in equilibrium with gaseous water vapor in an enclosed container. Okay, which phase, gas or liquid, is the chemical potential? In which phase is the chemical potential of water higher? Is it in the liquid phase, the gas phase, or is it the same in both? Well, if they are at equilibrium, what does that mean? That means the tendency for water molecules to leave the liquid and go to the gas phase is equal to the tendency of the gas phase water molecules in the gas phase to go back to the liquid, to go to the liquid phase. Equal tendencies. What that suggests then is that the chemical potential in the liquid of water molecules in the liquid would be equal to its chemical potential in the gas. Okay, so you can see that's a very important condition for equilibrium. If we have a species that can be in two phases, for those two phases to be at equilibrium, the chemical potential of that species must be the same in both phases. Now, let's look at the same scenario, but this time, okay, we're going to introduce solutes to the liquid. Okay, in which phase now will the chemical potential of water be higher, at least momentarily? Because if you remember, as we said, at equilibrium, the chemical potential of water will be the same in both phases. So at the moment you added the solutes, let's say, at that particular instant, what happens to the chemical potential in the of water in the liquid? So if I add solute here, so I have water here, a liquid, and water vapor, gas here. If I add solutes to this, what happens to the concentration of water here? So you say your concentration of water is going to drop. So your chemical potential of water in the liquid will momentarily drop. Okay? So momentarily, chemical potential in the liquid is going to be less than the chemical potential in the gas. And so what's going to happen? Molecules of water will leave the gas where it has a higher chemical potential and go to the liquid. Okay, so what happens to the pressure of the water vapor? The pressure of the water vapor is going to drop. Okay, and so eventually when it's dropped enough so that both chemical potentials, and then as the water molecules enter the liquid, that will sort of cause the concentration of the water to increase in the liquid. Okay, so that will make the chemical potential go up. So eventually what happens is the chemical potential in the gas will drop enough so that when equilibrium is reestablished, then chemical potential of water in the gas will be equal to its chemical potential in the liquid. So the net effect of adding a solute to your water, to your liquid water, is to lower the vapor pressure. Okay, so you lower the pressure of water in the gas phase. So if you introduce solids, if solids are introduced into the liquid, the what will happen? In which phase will the chemical potential of water be higher? Momentarily, it's going to be higher in the gas, but eventually, once equilibrium is reestablished, it's going to be the same again. Okay, and the way it's going to be the same again is because the chemical potential of water is going to drop for both the gas and the liquid. Here's another example. Consider the figure here where you have ice in equilibrium with pure liquid water at 1 atmosphere pressure, a thermally insulated container. Which one has a higher chemical potential? Ice at 0 degrees or liquid water at 0 degrees, or is it the same? Well, ice and liquid water will be at equilibrium at 0 degrees Celsius. There's going to be an equal tendency for melting and freezing, right? So chemical potential would be the same for both. But what happens if we introduce a solid? Let's say we add sodium chloride to your liquid water. What will happen? By adding a solid to your water, you lower the concentration of the water, right? So that causes the chemical potential of the water in the liquid to drop momentarily, okay? So what will happen is now it will momentarily your liquid chemical potential in the liquid would be less than chemical potential in the ice. And so water molecules will leave the ice, so your ice will melt. Okay? And as water molecules go towards the liquid phase, then the chemical potential of the liquid phase will start going up. What about this figure right here? What if you were to mix ice at 0 degrees Celsius with water at 20 degrees Celsius? What do we know? We know that chemical potential in the ice must be higher than the chemical potential in the liquid because we know your ice is going to melt. Whereas, so that's at 20 degrees, right? At 0 degrees, chemical potential of ice is equal to chemical potential of the liquid. So what does that tell you then? That the chemical potential of the liquid then must be higher at 0 degrees than it is at. So it will drop as you go from 0 degrees to 20 degrees. So it's higher at 0 degrees than it is at 20 degrees. Okay? All right. So we can summarize the behavior of chemical potential with this diagram right here. Here's a plot of chemical potential versus temperature for ice and liquid water. Which of these two curves you think represents ice and which one represents water? Which one represents ice? The steeper curve, this one? This one is a steeper curve, right? And the less steep curve is B. Well, to figure this out, let's try to understand, first of all, what does the intersection of the curves mean? Okay? This point right here, where the two curves intersect, would suggest that at this point, chemical potential of A, okay, of water in phase A would be equal to its chemical potential in phase B. So that means the same chemical potential, then you must be dealing with a system here at the melting point of water, right? Or at the freezing point of water. So this must be at 0 degrees Celsius. Okay, chemical potential is the same. What do we know below the freezing point? This is the freezing point, right? Or the melting point. Freezing point of the liquid, melting point of the ice. What do we know below at that temperature? We know below that temperature that liquid is going to freeze, right? So that means below that temperature, mu of the liquid must be higher than mu of the solid. So that means this curve right here, the dashed line, would represent the liquid. And this solid line down here would represent the solid. Here you're going to see a drop in the chemical potential below, and going from liquid to solid below the melting point or below the freezing point. And you can make a similar conclusion above the melting point. Let's take a look at this situation right here. We're at a temperature above the melting point. What do we know above the melting point? Your solid is going to freeze, right? Your solid is going to melt. So if you go from solid to liquid, that means chemical potential of the solid would be higher than the chemical potential of the liquid. So this must be the solid then, and this must be the liquid. So again, you can see it's this line right here. The less steep curve is the one that corresponds to the solid. The steeper curve would correspond to the liquid. Here's a figure that illustrates the temperature dependence of the chemical potentials of ice, pure liquid water at 0 degrees, and liquid water in an aqueous solution at 0 degrees Celsius. Okay, which curve represents, well, versus temperature actually. Which curve represents pure liquid water? Okay, so based on the previous slide, we said that, okay, liquid would be steeper than solid, right? So this is solid. Okay, so that's for the ice. So where they intersect, that's your melting point or freezing point, and those are the two possibilities. So which of these two, so both of these would be liquid, would be the chemical potential of the liquid. In which case do you have the chemical potential of a pure liquid water, and in which case are we talking about the chemical potential of water that's in an aqueous solution? Well, what did we say? Chemical potential in a pure liquid, we say, pure liquid would be more concentrated, we say, with that liquid compared to the solution, right? So chemical potential in the pure liquid would be higher than the chemical potential of your water in solution. Okay, so this must be the pure liquid right here, the dashed line. The dashed line would be water in aqueous solution. Okay, why? Because let's pick any temperature right here. Okay, this one right here, your liquid, pure liquid, will have a higher chemical potential than the contaminated liquid. Right? So if you pick at any given temperature, the chemical potential of the liquid, pure liquid, would be higher than that of the water molecules in the solution. So, as a result, can you use this to explain freezing point depression then? By contaminating your water, what have you done? You've moved the intersection, okay, you've moved the intersection between the solid and liquid chemical potential curves to lower temperatures. So in effect, what you have done is you have lowered the freezing point of your liquid. So that explains freezing point depression in terms of chemical potential. Okay, here's another one. This illustrates the temperature dependence of liquid water, water vapor, and liquid water in aqueous solution. And you can use this to explain boiling point elevation. Well, what do we know? Okay, where are the boiling points here? It would have to be here, okay, and here. So this would have to be the liquid, chemical potential of the liquid, and this would have to be the liquid, and this would have to be the gas, chemical potential of the gas, okay, would be lower than, this would be the pure liquid, right? And this is the liquid that is contaminated, so this would be in solution. Why is that? We said that by contaminating your liquid, you're lowering its chemical potential. So you're going from a higher chemical potential in the pure liquid to a lower chemical potential. Okay? And so you can see that the assignments that would be consistent with what we know would be, this would be pure liquid. Okay, this would be aqueous solution. So this is pure water right here. This is aqueous solution, and this would be the gas. So this intersection right here is the boiling point. Okay, where chemical potential of the liquid is equal to chemical potential of the gas. What happens below the boiling point? Chemical potential of the gas would be higher than the liquid. So the chemical potential of the gas is higher than chemical potential of the liquid at T less than the boiling point. Right? And similarly, at temperature above the boiling point, okay, chemical potential of the liquid is lower than that of the gas. So the gas will what did I say? Okay, chemical potential of the gas would be higher than that of the liquid. Okay, the gas will condense below the boiling point. Above the boiling point, your liquid will vaporize. Chemical potential in the liquid would be higher than in the gas. All right. And so how does this explain boiling point elevation? Well, if you've contaminated your liquid, like I said, you would lower its chemical potential. Okay, so this is pure, and this is aqueous solution. And so what happens ultimately is you increase the boiling point of your liquid. So this explains boiling point elevation in terms of chemical potential. Now, earlier when we talked about Gibbs energy, we introduced chemical potential as the molar Gibbs energy for a pure substance. So whatever the Gibbs energy is divided by the number of moles, that gives you the molar Gibbs energy. That's the chemical potential. Where does that come from? In general, we can define chemical potential as the partial molar Gibbs energy if you're dealing with a species that is part of a mixture. So if you're dealing with a mixture, for a component of a mixture, okay, let's say A is a part of a mixture, then the chemical potential of species A in this mixture would be the partial derivative of the Gibbs energy of the system with respect to the number of moles of A. In other words, how the Gibbs energy would change as a result of a change in the number of moles of A, provided you hold temperature, pressure constant, as well as all the other moles of substances in your system are held constant. Okay, so another way of writing this is to say chemical Gibbs energy of A, and then you put a bar on top of that, makes it we call it a partial molar Gibbs energy. All right. Now, where does this definition come from? If you recall, from our fundamental equation, we said U is a function of entropy and volume. The natural variables we say for internal energy as entropy and volume. And our fundamental equation is du equals TdS minus PdV. Now this equation holds for what we would call a closed system where nothing's changing. Okay? But if it's possible for composition to change, or if we're dealing with changes involving changes in composition, you have what's called an open system, then your U has to be expressed as a function of not just entropy and volume, but also the number of moles of each of the components. So moles of component 1 and 2 would be moles of component 2, and so on. So if you take the differential of U, then it becomes TdS minus PdV, okay, plus additional terms because of these additional independent variables that you can add to your expression. So mu1 dn1 plus mu2 dn2, and so on and so forth. And so at equilibrium, that's going to have to be equal to 0 at constant S and V. Yeah. So that's just du. So what is mu1 here? Mu1 is just partial derivative of u with respect to n1, holding S and V constant, as well as the other moles in the system, the moles of other species in the system. So I'm just going to call it n sub j, j not equal to 1. Okay. Chemical potential of species number 2, component 2, would be partial derivative of internal energy with respect to moles of component 2 at constant S, V, and number of moles of the other components, so Nj, where j is not equal to 2, and so on. Now, it's easy to show, okay, that the G would be equal to, if you recall, if du is TdS minus PdV, our definition of G is such that dG is minus SdT plus VdP for a closed system, right? So you have to carry over this extra terms there for your expression for dG if you're dealing with an open system. So this suggests then that mu1, chemical potential of species 1, would be the partial derivative of G with respect to N1. This time, the variables you're holding constant are temperature, pressure, and number of moles of the other components. So we'll just call them n sub j, j not equal to 1. Okay? Now, this is more important to us because we like to deal with things at constant temperature and pressure. And so that's why we define chemical potential as a partial. We often identify it as a partial derivative of G with respect to number of moles because that's what we'll be dealing with most of the time. Okay? So, partial derivative with respect to number of moles, if you're holding temperature and pressure constant, in general, any partial derivative, okay, with respect to number of moles that involves constant temperature and pressure is called a partial molar quantity. So chemical potential is also known as a partial molar Gibbs energy. All right. So I just want to make a note here so that you don't mistake partial of U with respect to N at constant S, V, and N as a partial molar internal energy. It's not. Okay. And the reason for that is you're holding S and V constant here instead of T and P. All right, let's just clarify what we mean by that. What would be your expression for mu1 in terms of H? If you go back to your expression for H, remember du is TdS minus PdV. And what was H? H is U plus PV. So dH would be TdS plus VdP. You switch roles for P and V, remember? But that's for a closed system. If you have an open system, then you would say dH is equal to TdS plus VdP plus mu1 dN1 plus mu2 dN2 and so on. So what is mu1? That's a partial derivative of H with respect to N1, holding entropy and pressure constant as well as the other number of moles, as the number of moles of the other components, n sub j, j not equal to 1. Okay? Now, what derivative would be called the partial molar volume of component 2 of a mixture? Partial molar volume. So, of component 2, so you would write that as V bar 2. Okay, that's what that means. The bar means partial molar. And so then you would say that would have to be the partial derivative with respect to the number of moles, since we're dealing with component 2. So it's with respect to the number of moles of component 2. But since this is a partial molar quantity, we have to say that the variables you're holding constant are temperature and pressure, and the number of moles of the other species in the system are also held constant. All right. So let's examine what happens now to the chemical potential at equilibrium at constant T and P. We're going to focus on equilibrium at constant temperature and pressure. And if you remember, we said G is minimized in that case. And so we say dG is equal to 0. Well, dG is negative S dt plus vdp plus mu1 dN1 plus mu2 dN2. If temperature and pressure are constant, okay, then dt is going to be 0, dp is going to be 0. So this expression right here on the right is just going to be equal to 0. So you say mu1 dN1 plus mu2 dN2 and so on will be equal to 0. So that is the condition at equilibrium at constant temperature and pressure expressed in terms of chemical potential. This is, of course, dG at constant temperature and pressure. Right? So let's apply that to phase equilibrium. Let's say you have two phases, okay, where you have liquid water in one phase and you have solid water in the other phase, so gaseous water, okay. Let's call this liquid phase 1 and the water, the gaseous phase 2. Well, what happens? At equilibrium, when you have your liquid and your gas at equilibrium, then you say mu1 dN1 plus mu2 dN2 is equal to 0. That's what we showed earlier, right? You have at equilibrium, when G is minimized, then chemical potential of 1 dN1 plus chemical potential of 2 times dN2 and so on would be equal to 0. Well, if you do, let's imagine we're transferring a small, imagine if we were to transfer a small amount of water molecules, let's say from phase 1, from the liquid to the gas, okay? Then whatever dN1 is, it's just going to be the negative of dN2, right? Okay? If you gain dN2 moles in the gas phase, you're going to lose negative. If you get 5 moles in the gas phase, you lose 5 moles in the liquid phase. So if dN1 is equal to negative dN2, then we can say then that mu1 dN1, okay, I'm going to replace dN1 by dN2, right? So I'm going to say this is mu1 times negative dN2 plus mu2 times dN2 is equal to 0. If that's the case, I can factor out dN2. I can say mu1 minus mu2 dN2 is equal to 0. This is my dG, right? Constant temperature and pressure. Well, that suggests that if I were to transfer a very small amount of water molecules from the liquid to the gas phase, then this expression will be 0. I've reached a minimum in my G. So that tells me that this expression right here on the left must be equal to 0. So mu1 minus mu2 must be equal to 0. That means mu1 must be equal to mu2. And that's essentially what we said earlier. Chemical potential of a species present in two phases at equilibrium will be the same in both phases. That's a condition for phase equilibrium.